Okay, welcome back. So I would like to introduce now the concept of linear map. Also known as linear transformation or linear operators in many other contexts. Okay, so it's the same thing. So transformation. Operator. And there's more names for that. The important thing is that it's linear. Okay, so given two vector spaces, okay, so let V and W be vector spaces, which means that they can be, that the elements of V and W can be summed together and can be multiplied by scalars. Okay, so the scalars are taken always to be real. Okay, as I've said earlier, this theory can be extended to other fields than R. Okay, for example, the fields of complex numbers or rational numbers, but we do it for R in this course. Okay, so we don't have to worry about other things. Okay, but everything I say here can be actually generalized quite easily to other fields. Okay, and suppose we have a map that goes from V to W. Okay, so a map, I'm going to call it A, that goes from V to W is so it takes elements V and returns their image A, V. Okay, it's called linear. If it conserves or if it preserves linear combinations. Okay, so essentially this can be summarized as follows. If you take two elements, say V and U, okay, and then you take a linear combination of this type, okay, but you can also take this is a bit redundant here, you don't really need it, okay, the important thing is that saying that you can add and multiply, but the tradition is that you multiply a second time, okay, it's a bit redundant, but it's okay, it doesn't matter. It will lead to the same concept, okay? But the important thing is that you can essentially extract these scalars out of the operator, okay? So that's essentially what linearity means. In fact, this is one part of linearity, it's called homogeneity, okay? So we have homogeneity, but also we have additivity, which means that this plus here can also be taken out of the brackets. So in fact, A can go inside the linear combination. That's essentially what linearity means. Yeah. Sorry, U. Okay, so that's basically the definition of a linear mapping. Okay, so usually when we have such a map, we don't write AV instead of AV to lighten up the notation, okay? And because this map is linear, it essentially means that it's kind of like multiplying, okay? So linearity is essentially saying that the behavior of this mapping is like multiplication, okay? Because we have this kind of distributivity of multiplication by A, okay? So in fact, we will see that that matrix vector multiplication is a linear mapping. Okay, we already know that, and we just have to observe it. Okay, so let's make as a very quick example. Okay, so example. Okay, let's take V to be R M. Let's take W to be R N. Okay, and let's consider A underline. So A underline is slightly different than than A, okay, but in fact we'll see here that there's a connection between the two concepts. Okay, so let's take A underline to be a matrix which has n rows and m columns. Okay, this is how we write them usually. Okay, this means that I'll remind you that A can be written explicitly as follows: as a bunch of entries, okay, which have a row index here. Okay, so that would be the first row. This would be the nth row. Okay, so we have n rows, and we have so that would be the first column. Okay, so I'm going to put the index above. So I index above for columns. This is the m's column, first row, and this is the mth column, nth row. Okay, so it's very confusing to say these things in public. Okay, but when you're doing this in the private office, then you can do it quite well. And the distinction between lower and upper indices is just something we do in this course, but in very many other contexts, people just write them both as sub-indices. Okay, it's the same thing. It's just this one. It's a bit easier to manipulate at a first approach. It also saves a little bit of space when you're typesetting these things. Okay. The example I want to do is the following. So the map defined by x in R. So this is going to be a column in with as many entries as there are columns in A. Okay, so this one here is in Rm. Okay, and it will be mapped to the multiplication of the matrix A with the vector x in Rn is linear. Okay, so this is an example, and in fact it's quite an important example of a linear map. Okay. Other examples involve other vector spaces. For example, we can take the huge vector space of infinite sequences in with real coefficients. Okay, so example 2. So this was example 1. Examples. This was 1. This is 2. Let's take Rn. Okay, I'll remind you, this is the set of all sequences A1, A2, A3, etc., such that AI belongs to R for all I in N. Okay, that's why we write it like this. R to the power n. It's also kind of like a generalization of these guys when the power becomes infinite. Okay, this is like the rigorous way of doing it. Okay, so there's nothing wrong with this space. We've actually studied it quite extensively in the first part of the analysis course, where we looked at sequences, when they converge, when they diverge, when they do strange things. They have ints, they have subs. So this is quite a useful space, okay? And there are transformations that I can do in this space that are linear. For example, let's consider the shift. Okay, so shift. Okay, so an upshift. Okay, so an upshift, or if you can put a hyphen if you want. Okay, so upshifting means that I'm moving the whole sequence up. Okay, so the upshift of, so this one here, let's call it A with an underline. Okay, so let's give it a name. Okay, so upshift I'm going to call S for shift. Okay, and up I'm going to say +1. Okay, so this is going to be a new sequence. Let me give it a name. Let me call it B. Okay, where each entry, the first entry of B is well, let's think about that a bit later. Okay, but the second entry of B is A1. Okay, and the third entry of B is going to be A2. Of course, I have to take care also of the first entry. Okay, usually, I mean, if this was a finite vector space, there's two ways of doing the shift. You take the last element of the vector and you put it first. Okay, so it's kind of like a cycle. Yeah, and that would be a fun thing to look at as a matrix. And in fact, what you will see is that you're going to have lots of ones on the subdiagonal, and then there's going to be a 1 popping up here. But you cannot do this in infinite dimensions, okay? So you cannot take the last element because there's no last element for a sequence that is infinite. And therefore you have to kind of invent something here. For example, you can put a 0, okay? So this is quite an interesting map, okay? So this is basically, by definition, so this is, if you want, by definition, S plus 1 of A 0 coordinate. Okay, so maybe we should use square brackets here to indicate that. Okay, so this is S plus 1, A, sorry, first, second, etc. Okay, so basically you can summarize all this by saying that Bn plus 1 is by definition An, and that's an upshift. Okay. The downshift is when you take the sequence and you shift it down, okay? So the downshift would be the same, so let's call it S minus 1. Okay, so S minus 1A is equal to some other element, let me call it C, or not to confuse it with B, okay? Where Cn minus 1 is equal A n. Mind you, this can be written also in the equivalent form as Bn equals An minus 1. So the upshift means that you're taking a minus 1 here. Okay, be careful. And the downshift means that Cn is equal An plus 1, because you're taking the one above and you're shifting it down. Okay, so the upshift and downshift, sometimes also called right shift or left shift, because people think in terms of rows. Okay, it depends how you like to think of numbers. Some people like to think of them growing, and some of them like to think of them going to the right. Okay, which is equivalent, of course. So these are linear transformations. Okay, because if you take a linear combination of say two sequences, okay, and we saw how to sum sequences and multiply them by scalars, then what you're going to get is the shift is going to operate in a linear way, okay, by checking that small rule that we had. Okay, so this is another example of linear transformations. And I do this example in an infinite dimensional vector space because we'll see that doing matrices in infinite dimensional vector spaces is not as handy and useful as doing them in finite dimensional vector space, because the theory becomes much more complicated and incomplete in some sense with respect to the theory of matrices, which are finite. Okay, of course you could do infinite matrices, and they are very useful objects. Okay, but the theory is not as satisfying. In fact, it's much richer than the one for finite matrices. It's just it's in some sense it's too complicated to be dealt with in such a fundamental course as ours. Okay, but it's good to keep in mind such things. Okay, let's do another example, a third example of linear maps. Okay, and this one is a bit surprising because it is in a finite dimensional vector space. It can be done also in infinite dimensional vector space, but I'm going to do it in a finite dimensional vector space to surprise you a little bit. Okay, because there's this conception that maps, linear maps, have to be given by matrices, but it's not by any means true. For example, the following example 3, in our good old friend P3, okay, consider the mapping which takes the derivative of a polynomial. Okay, so consider D, okay, so I'm going to call it D, that goes from P3 into some other vector space. It could be P3 itself, okay, so we can take P3. Okay, but if we think about it, derivatives of third order polynomials, the most economical one to put here could be also P2. Okay, so this is a question of choice. Okay, it depends on you how you want to phrase things. But if we put P3 here, we would be like a bit wasting space because we would do something redundant. Because we know that polynomials of degree 3, when you differentiate them, they become polynomials of degree 2 at most. Okay, so if we have a polynomial f here, okay, we associate to it the derivative. Okay, so we define df in P2 such that df of x, okay, so df of x is nothing but d dx. So this is the sign of differentiation, okay, of the polynomial f of x. Okay, so for example, if f of x is, I don't know, 3x cubed plus 1/2 x squared minus 1, okay, then df of x is a polynomial that is given by 9x squared, okay, because the derivative of this one here, plus x, and the minus 1 is zapped away by differentiation because it's a constant. Okay, so differentiation here is with respect to x. Okay, you have to be careful what we're differentiating with respect to. Okay, and this is basically what you get here. Okay, so this is a mapping which is well defined for any polynomial. In fact, you could do it in general. You could define it in an algebraic way by saying if f is f of x, say, is, as we wrote it before, as a summation of the ci, I goes from 0 to 3 of this form here, then df is nothing but the summation for I that goes from 0 to 2, okay, because we're going to have one less index, okay, and here the ones that survive are the ones that act on the non-constant monomials. Okay, so we get ci plus 1, and here we get x to the power I. Okay, so this is what we get, and we should not forget to multiply with I, because that's what happens. Okay, so with I plus 1, sorry, because I'm missing from 0. Okay, so this is what I should be doing here, multiplying with I plus 1. So sorry about that. Okay, so you can check very quickly that this is just the same thing as this. Okay, it's just an algebraic way of defining the derivative. Okay, so for polynomials, their derivatives are so easy that there's an algebraic way of doing it. Okay, so it could be just somehow imposed. Of course, in calculus, we see that the derivative has also a meaning as the limit of the difference quotient. Okay, but what we're doing here is purely kind of formal manipulations, okay, or algebra of derivatives. Okay, and it's a nice exercise to check that, in fact, this map here is linear. In fact, here we recover some of the rules of differentiation. Okay. And this is linear, so D is linear. because, remember, if you take the derivative of a linear combination, so you take a constant, lambda, you multiply polynomial f by it, okay? And you take another constant, say mu, and you multiply the polynomial g of x. And you take the derivative, then these lambdas and mu's can go outside the bracket, and this d can hit the f and g individually to get you the same result. In fact, this is the rule that you use when you're differentiating. Okay, so this shows that, in fact, this mapping here is linear. Okay, so this one here is linear. And in fact, this example can be extended to a space that is absolutely infinite dimensional. Okay, no finite dimensions, by just taking all polynomials. Okay, so you can take the derivative as mapping from all polynomials of any degree, and you return polynomials of any degree. At this point, you see that this kind of like lack of symmetry between the domain and the codomain of this mapping D goes away, because you cannot put a bound here, okay, because these are infinite. Okay, in other words, infinity minus 1 is infinity. Okay, so this is the cheeky way of saying it. Okay, but we don't have to say that. Okay, we don't have to worry about infinity in such a vague way. Okay, because what we're doing here is fully rigorous. Okay, so the same applies. Of course, you would have to do this for a generic I. Okay, and here you would realize that all you need to do is to go down by one index. Okay, there's two ways of doing it. You can do it for I going from 0 to I minus 1, or you can start at 1 and go all the way to I, and then you shift the indices here. Okay, because I've written it this way, I'm going to keep this convention here. Okay, it's a bit messier, but it's okay. It still works. Okay, so this definition here is equivalent to this one. This example still holds. Okay, and D is linear because we have this rule here. Okay, so in fact, linearity here has nothing to do with the fact that we started with a finite dimensional vector space. Okay, and things can be done in infinite dimensions as well. Okay, so the last example I would like to do is more geometric. Okay, because linear algebra is very useful in geometry. Okay, so what I would like to do is talk a little bit about plane geometry here. Okay, and look at some transformations which are linear in the plane. So linear transformations geometrically, they conserve linear features. So for example, if you have a plane or a line and say in Euclidean space, and you apply a linear transformation to it, what you obtain is again a line or a plane. Okay, so this idea of linearity is conserved. Okay, that's essentially what linear transformation is. Okay, so my fourth example here, okay, is in R2. So we already seen that matrices of the form, I don't know, let's call them A, B, C, D. Okay, I'm writing A, B, C, D here for a reason that's going to be apparent later on. Okay, for consistency. There's no like rule saying that I have to write a matrix row-wise. Okay, I can write it column-wise in many respects. That's quite important to think of it as being a row of columns rather than a column of rows. So this one here is always a linear map. Okay, so A, C multiplies xy. This returns, of course, ax plus cy, and this returns bx plus dy. Okay. So as you've seen before, this is a linear map. Okay. So yields a linear map. We're going to see very soon a theorem that says that also the converse is true. So any linear map can be written as a matrix times vectors. Okay, so a given fixed matrix times the variable vector. Okay, and in fact that's the basic theorem in matrix analysis or matrix algebra, because it tells you essentially that if you study matrices, it's the same thing as studying linear maps on finite dimensional vector spaces. Okay, that's why they're so important. Okay, but before we do that, let's try to think about maps in a geometric way. Okay, and a nice type of maps are dilations. Okay, so a dilation means that you take something and you just zoom it in or out. And we've already seen that this can be encoded just by multiplying with a scalar. But in terms of matrices, multiplying with a scalar, so if you take a scalar, a fixed scalar, lambda, okay, and you multiply a vector x in 2 dimensions, okay, so let me write it as xy. So by definition, this is lambda x times lambda y, right? But if we look at this expression here, we see that this is nothing but saying that we have a matrix where the entry A is equal lambda, and the entry D is also equal lambda. So in fact, this dilation, okay, this multiplication with the scalar, or scaling, if you want, can be written also as lambda naught lambda xy. Of course, this is kind of silly, right? Because you're wasting lots of chalk in order to do that. Okay? But it just connects the idea that matrices can represent certain type of linear maps. Okay, but this is kind of like a very easy one to write. Okay, other linear maps that we can have are, for example, rotations. Okay, so rotation, as you know from physics, is a rigid transformation. Okay, it does not change the length of things. It does not alter the angles. Okay, it keeps everything the same. All it does is just turns things. Okay, for example, this vector here. Okay, let's call it xy. It would not change length if you rotate it. Okay, so say you rotate it by 45 degrees. Okay, by pi forward. Okay, then it would be here. Okay, it would be a circle. It takes it from here to here. Okay, and this would be pi fourth. Okay. Now, if you know some trigonometry, you can actually show that what's going on here is this. Okay, so let's call this new vector. Let's call it coordinates v and w. Okay, and I'd like to understand how to connect the v and w to the x and y. Okay, in order to do the rotation. Okay, so now we know that x and y form some angle. Let's call it alpha. Okay, so here I'm doing trigonometry. If you don't know trigonometry, don't worry too much about this example. Just focus on the outcome. Okay, but here I'm going to explain why the outcomes comes from like basic trigonometry. Okay, so you already know that the x is nothing but the length of the vector xy. Okay, so let's call the length of the vector xy. Let's call it L. Okay, so let L be x squared plus y squared, and then you take the square root of that. Okay, because x and y are real numbers, x squared plus y squared is going to be a non-negative or positive real number if you want, and therefore I can take its square root, and its square root is defined to be the unique positive number such that L squared is equal to x squared plus y squared. So this x here is nothing but L times cosine alpha, where alpha is this angle here. Okay, and the same thing for the y. This is the sine of alpha. Okay. Now I know that the new vector, so the outcome v, is going to be of the same length. So I'm going to use L again because it's a rigid transformation, so L doesn't change. Okay, so it has the same length. But the angle with the horizontal axis has changed. Okay, and let me call the new angle beta. Okay, so let me take some color chalk here. I call this one beta. Okay, so this is L cosine beta, and W is L sine beta. Okay, this looks like a mess, and you have to be very careful because the functions sine and cosine are not linear. Okay, so linearity here has nothing to do with the fact that cosine or sine might or might not be linear. We're going to see linearity how it comes from, but this is just a small warning here. Okay, so warning. The functions sine and cosine as functions that go from R into R. If you know some analysis with trigonometric functions, I'll just remind you how things look like. If you don't know that, then this is a good prelude to things we're going to do in analysis. This would be 1 and this would be -1 here, okay? And the sine function is basically, it starts at 0, okay, because the sine is the projection on the y-axis, okay? So it starts at 0 when I'm here, okay? So the sine of this, of the angle 0 is 0, okay? And then it goes all the way to 1 when the angle becomes pi half, okay? So usually angles are used in radians, okay? So radian, to remind you, is simply the length of the curve of the arc. It's the length of the arc on a circle of radius 1, okay? Corresponding to the angle that is being described, okay? So these are angular functions, if you want, okay? And this is how the sine looks like, okay? It goes up here, and then it starts going down, and then becomes 0 again when you do a half turn, yeah? When you end up being on the other side of the axis, okay? And then the sine becomes negative because you end up going down, and again here we get 3 pi half, and it becomes -1, and so on and so forth. Okay, so this is a sine function, and it is symmetric and odd. So it's a symmetric, it's an odd symmetric function. Okay, so that's the sine, and the cosine just looks the same except it's shifted by a phase of a quarter turn, yeah, or by an angle of pi half. Okay, so that's called also phase. Okay, so that's basically the cosine. Okay, so the blue line is the cosine function of x, and the white line is the sine function of x. And as you can see, the graphs of these functions are far from being lines, and therefore these functions here are not linear. Okay, so basically the warning is that are not linear, meaning that we don't have this. So if you apply cosine to a linear combination, say lambda alpha plus mi beta, this is not equal to the cosine of lambda times cosine alpha plus cosine mi times cosine beta, or even worse, it's not even equal to this. Yeah. So these are not linear functions. Okay. So even writing this kind of nonsense is not very useful because it's not saying that things are not different. It's enough to make one example to see that. Okay, but you see it from the picture essentially, because otherwise the graph should be a line. Okay, that's a small exercise to show that all linear maps that are going from R into R are essentially have the graphs as lines that go through the origin. Okay, having said that, now I still want to show you that the map that transforms the rotation is a linear map. Okay, this is quite an interesting fact. Okay, so let me try to understand that from what I've done so far. Okay, so let me erase this warning here. Okay, and let me look at the third angle that we have here in the picture. Okay, so we have a third angle which is, I'm going to do it in green. Okay, is this pi-4, right? Which is the amount of rotation that I'm putting. Okay, and there's a connection between the pi-4 and the alpha and the beta. Okay, so let me call this pi-4. Let me give it a short name. Let me call it theta. Okay, so in this example, theta is equal to pi-4, but we could be doing this for any angle theta. Okay, I just decided that theta is pi-4 to draw the picture. Okay, so for that angle theta, I know that theta, in terms of angles, in angle algebra, is the angle beta minus alpha. Okay, that's basically what theta is, because alpha plus theta is equal beta, and therefore theta is beta minus alpha. So it's like to get to theta, all you need to do is you rotate by beta and then you subtract alpha. Okay, so you would get the angle theta, which signifies this green guy here. Okay, and by the addition rule for cosines. So cosine, we said, is not linear, but we know that the cosine of alpha minus beta. So you might remember this from your early trigonometric courses. Okay, this is the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. That is true, but that's not the one I need here. Okay, so the one I need here is another one. It's the same formula, but it's applied to a different angle here. What I would like to do is express the new angle or the new cosines and sines in terms of the old ones, and in terms of the theta. So in fact, what I'm going to do here, I'm going to write the cosine of beta. Okay. So the cosine of beta, because beta is equal theta plus alpha, can be written also as follows. It's theta plus alpha. Okay. So here we have to modify our formula. Because we have a plus here, we get, you might remember this kind of peculiar phenomenon, that if you have the plus inside the cosine, that what you get here is a minus. Okay, that's trigonometry. Okay, and there's a nice way of showing this formula by using triangles. Okay, I'm not going to do that here. This is not the topic of the course. I'm assuming you know this formula, and if you don't know it, you can look it up on Wikipedia. And here we have cosine of theta times cosine alpha, and sine theta sine alpha. Okay? So this is cosine of beta. So in fact, V, here, by using that formula there, I see that V is equal to L times cosine theta cosine alpha minus sine theta sine alpha. Okay, and W is by using the sine rule. Okay, so we know that sine of theta plus alpha is equal to this time the sine, you might remember this, conserves the sign. Okay, so we get a plus here, but we cross the terms. Okay, so we have sine theta cosine alpha, and we have cosine theta sine alpha. Okay, so I'm writing it in such a way that the cosine alpha and sine alpha are on top of each other. Okay, because I know that that's the neat way of writing it. Okay, if you're doing this the first time in your life, you might do it more messily, but it doesn't matter. In fact, I would advise you to do it again without thinking at these notes, because that's a good exercise. Okay, again times L. Okay. Now, if we explicit this expression a bit more in terms of the previous x and y. Okay, so in order to get x and y here, all I need to do is to multiply L with cosine alpha. So if I multiply L with cosine alpha, I'm going to get the x, okay, because that's what x is. So I get cosine theta times x. And here I get minus sine theta times y. And this is equal, in the same way, to sine theta times x plus cosine theta times y. So what looked like a big mess initially, now it's starting to look quite simple. In fact, VW can be written as a matrix times xy, where the matrix is extracted from that. Okay, now remember, theta in our example is pi/4. Okay, I wrote theta because it's easier to write than pi/4 all the time. Okay, but I could have written pi/4. So the matrix is actually constant. Okay, it's not changing with respect to the variable x and y. Okay, so the variable x, y is any generic point in the plane is being rotated to its output, which is VW. Okay, but the rotation is always by the same amount. It's always by pi/4. Okay, so this matrix here is not variable. Okay, it's a constant in that sense. Okay, it's a constant with respect to this variable. So it's a constant matrix. It's always the same matrix that multiplies the variable x, y. And this is essentially telling me why the rotation is a linear transformation. And geometrically, this can be you have an intuition for this because rotation will not change lines into curves that are not straight. Yeah, so in non-straight curves, and that's essentially why you have linearity of rotations. Okay, so this is a rotation of an angle theta in a counterclockwise direction. Of course, you could do it also in a clockwise direction. Okay. So nothing prevents you from rotating in the other direction, and you will see that the only thing that changes is the sign of the sign. Okay, so you get a minus here and a plus there if you're going in the clockwise direction. And what is interesting to see is that if you multiply the two matrices together, what you will get is the identity. And in fact, this conforms to the fact that the inverse of this rotation is the rotation by the same angle in the other direction. Okay, truly, this is like the undoing of that operation, and we'll see that inverting matrices is essentially amounts to inverting the linear map that takes those vectors into other vectors. Okay, so this is just an example of rotations. Okay, so this is rotation of xy by theta in counterclockwise sense. Okay, so that's it. Thank you very much.